So I told you that in an atom, this is an atom.
Yeah.
And in an atom, at the center, there is nucleus. And I also told you that in the Rutherford's model of atom, I told you that there is a center in the atom. And in that center, there is a positive charge and large mass is concentrated in a small space. And that is called as the nucleus. So basically, this hole is the atom. An electron is revolving around the nucleus. In circular orbit, electron is revolving around the nucleus in circular orbit. And this is the nucleus. And nucleus is having the positive charge. So entire mass and positive charge of an atom is concentrated into very small volume called nucleus. First point. So entire mass of the atom and entire positive charge of the atom is concentrated into very small space called nucleus. Radius of the atom, I told you that in the last class also, is approximately 10 to the power minus 10 meter. And radius of the nucleus is found to be 10 to the power minus 14 to 10 to the power minus 15 meter. So you can say nucleus is much smaller than the atom, or you can say nucleus is approximately 10 to the power 4 or 10 to the power 5 times smaller than the radius of the atom. Now we will discuss the nuclear structure. So nucleus is basically made up of neutrons and protons. Inside the nucleus there are neutrons and there are protons, and neutrons and protons combinedly we call nucleons. Neutrons and protons are called as nucleons. Now proton is basically the hydrogen nucleus. Proton is basically the hydrogen nucleus. We say proton is the proton, but we can denote proton by the hydrogen nucleus. In hydrogen nucleus there is only one proton. Now charge on the proton is equal to the charge on the electron, but for proton the charge is positive, that is plus 1.6 into 10 to the power minus 19 coulomb. Mass of the proton is 1.6726 into 10 to the power minus 27 kg, and this is equal to 1 AMU. Mass of proton is equal to 1 AMU, atomic mass unit, and this is represented by 1 mu also. Symbol of proton is this hydrogen. This is H, 1 and 1. This is representing the charge, and this is representing the mass. This is representing the charge, this is representing the mass. Okay. So hydrogen atom, what is the atomic number of hydrogen? 1?
Yes.
Atomic number of hydrogen, Z is known as the atomic number 1. Atomic number of any element is equal to number of protons. Number of protons. And this is the hydrogen. Then in hydrogen there is only one electron also. Okay. So basically in hydrogen there is only one electron, there is only one proton. If you will remove that electron, so what will be inside? Nucleus, and nucleus have only one proton. So this is the hydrogen atom, and this is the nucleus of the hydrogen atom having one proton. Okay. So this is the symbol of proton, H11. And this is the hydrogen atom, and this is the nucleus of the hydrogen atom. This is the nucleus of the hydrogen atom, and inside the nucleus of the hydrogen atom there is only one proton. That is why I was saying proton is also, we say sometimes proton as hydrogen nucleus, because inside the hydrogen nucleus there is only one proton. Now after that, neutron. What is neutron? Charge on the neutron is 0. This is neutron. Mass on the neutron is this 1.6749 into 10 to the power minus 27 kg. Now 1.6749, this is the mass on neutron. Mass on proton 1.6726. So basically you can say mass on neutron is slightly greater than the mass on proton. Mass of proton. So mass of neutron is this, and this is approximately equal to 1 AMU. Okay, approximately equal to 1 AMU, because this mass and this mass are nearly same, and this mass equal to 1 AMU. So this mass we can say nearly equal to 1 AMU, and symbol of neutron is this, N0 1. Charge on neutron is 0. Okay, mass of neutron is 1 AMU. This is representing the mass. We will study this in the next topic. Charge, mass, number of proton, number of neutron. Okay. After that, we will discuss atomic number, mass number, and atomic mass. Atomic number, mass number, and atomic mass. So what is atomic number? Atomic number is represented by Z. Atomic number is basically the number of protons inside the nucleus. Number of protons inside the nucleus. What is the mass number? Mass number is the number of protons plus number of neutrons. Number of protons plus number of neutrons. And what we call protons and neutrons? Nucleons. So you can say number of nucleons.
Okay.
Mass number is a number. Like you can say mass number is 8. Mass number is 14. So it is a number.
Yeah.
After that, there is a term atomic mass. Atomic mass. So atomic mass, what I told you about the mass of the atom, we consider entire mass. We consider entire mass of the atom is concentrated in a nucleus. So basically, we will consider atomic mass is basically the mass of nucleus. Why we are considering the mass of nucleus? Because entire mass is concentrated in a nucleus. We are just neglecting the mass of the electron, because electron is having very less mass, 9.1 into 10 to the power minus 31 kg. That is very, very less.
Yeah.
Okay. Yes. So mass of the atom, atomic mass is equal to mass of nucleus. And what is the mass of nucleus? Nucleus is made up of proton and neutron. So we will say mass of protons plus mass of neutrons. Okay. Mass of protons plus mass of neutrons.
Yeah.
So mass of number of protons plus number of neutrons into 1. Basically, try to understand this. What they are? What is this? Basically, we are calculating the atomic mass, and atomic mass is what? Mass of nucleus. Mass of nucleus is determined by the how many number of protons are there and how many numbers of neutrons are there. Okay. Yes. So basically, what we will do, first we will calculate how many protons are there and how many neutrons are there. And I told you the mass of proton and mass of neutron is nearly same. That is 1 AMU. So we will add the number of protons and number of neutrons and multiply it by 1 AMU. So mass of nucleus is equal to the number of protons plus number of neutrons multiplied by 1 AMU. Okay.
Okay.
Multiplied by 1 AMU. So this will be the atomic mass. This will be the atomic mass. Mass number is represented by A. And what is mass number? Number of protons plus number of neutrons. So number of protons plus number of neutrons can be written as A. That is mass number. Can be written as mass number. And this mass number is multiplied by 1 AMU. And mass number is A into 1 AMU. So atomic mass is A into 1 AMU. Yeah. Atomic mass is equal to A into 1 AMU. You have to remember, what is atomic number? Number of protons in nucleus. What is mass number? Number of protons plus number of neutrons. Number of protons plus number of neutrons is the mass number. For example, and in 1 AMU there is this kg. Suppose this is the element X.
Yeah.
So this is the atomic number Z and this is the mass number. That's how we represent an element. So Z is the atomic number, and what is the atomic number? Number of protons. What is the mass number? Number of nucleons. Nucleons means number of protons plus neutrons. Okay.
Yeah.
Now, this is the oxygen. In some books, you will find oxygen element is written as 8, 16, and in some books, here is 8, here will be 16.
Yeah.
So this 8 lower side is the atomic number, and here is the mass number. So this 8 is the atomic number, 16 is the mass number. Okay. So if you have to find suppose number of protons, so number of protons will be atomic number.
Yeah.
Z, that is equal to 8.
Each,
Number of nucleons, if you want to calculate, that is equal to mass number, that is equal to 16. If you want to calculate number of neutrons, so you know that protons plus neutrons is equal to the mass number, and number of neutron will be A minus P. Or what is number of proton? A minus C here. Suppose you want to calculate number of neutrons.
Yeah.
Number of neutrons. Number of neutrons you want to calculate, okay? So we know that mass number is equal to number of neutrons plus number of protons.
Yeah.
So number of neutrons can be written as A minus P. And we know that number of proton is equal to Z.
Yeah.
I can write A minus Z. So the answer will be 16 minus 8. 8 protons are there. So in this, 8 protons are there. Okay. Now, if this is the question, in this question, if we want to find, this is carbon 6, 13. So how many protons are there? Atomic number.
Yeah,
Atomic number,
6.
yeah, 6.
Yeah.
How many nucleons are there? Nucleons. Nucleons are there. We know that nucleon, number of proton plus neutron. So basically, the nucleons is equal to the number of
Yeah.
protons plus
Nucleus.
number of neutrons,
Neutron.
and that is equal to A, and A
Yeah.
is 13. Now, if we want to find the number of neutrons, so 13 minus 6.
Yeah.
Number of neutrons.
7.
Yeah. 13 minus 6. That is equal to 7. So atomic number, number of proton, mass number, number of protons plus neutrons. Now we will discuss the classification of nuclei. Classification of nuclei. So classification of nuclei, we have 3 types. In 3 types we can do the classification of nucleus. So first is the isotopes. First is the isotopes. So isotopes are the atoms of same element whose nuclei have same number of proton but different number of neutrons.
Yeah.
With example, you will understand. Okay. So basically, in isotope, atomic number will be same, but mass number will be different. Atomic number will be same, but mass number will be different. For example, take the example of hydrogen. Take the example of hydrogen. So this is 1H1, 1H2.
Sir.
Hello.
Sir, you're lagging, sir.
My voice is lagging.
Yeah. Video. Yeah. Both. Sir.
Just a minute. Just a minute. Okay. So hello.
Yes, sir.
It's fine now.
Yeah.
So isotopes, atomic number same. So see, atomic number 111 same, mass number different 1 2 3 isotopes. Okay.
Okay.
Chlorine, these are the two isotopes. Okay. Isotopes means atoms of same element. Element, what is the element here? Chlorine is the element.
Yeah.
And these are two different atoms of chlorine.
Yes.
And one is 1735, another is 1737. So what is the atomic number of this chlorine atom? 17.
17.
What is the atomic number of this chlorine atom? 17. Means
17.
atomic number same. And what
Yeah.
is the mass number? 35, 37. Mass number different.
Yeah.
So this is also a isotope.
Yeah.
This is not, mean these are also isotopes. So these are the isotopes of chlorine.
Yeah.
And these are the isotopes of hydrogen.
Yes.
Isotopes of hydrogen. After that, okay, in nature, if you see, chlorine is chlorine atoms. You will find the chlorine atoms, one in this form, another in this form. So in nature, chlorine is found in two forms, or hydrogen is found in three forms.
Yeah.
So one chlorine atom is having a mass of 35, another chlorine 35 AMU, and another chlorine atom is having a mass of 37 37 AMU.
Yeah.
So if I want to find the average mass, means how I will determine the mass of chlorine. I will determine the mass of chlorine by taking the average of this and this. Okay. So basically this is done by first we will see in how much fraction both the elements are found in nature, and accordingly we will decide. Okay. So here is the next topic, fractional atomic mass due to isotopes. Why the fraction? We are calculating the fractional atomic mass due to the isotopes.
Yeah.
With example, it will be clear. So average atomic mass or fractional atomic mass is given by A1, N1, A2, N2, A3, N3. A1 first atomic mass of first isotope, A2 atomic mass of second isotope, N1 fraction of first isotope, N2 fraction of second isotope. Now with example, it will be clear. In nature, this chlorine is found 75% chlorine is found in this form. 25% the chlorine is found in this form. If you want to calculate the average atomic mass of the chlorine, then you will apply this formula, A1N1 plus A2N2. What is A1? A1 is the atomic mass of first chlorine atom, 35. N1 is the fraction. N1 is the fraction. Fraction is it will be 75 by 100 plus A2N2. A2 is 37. N2 is fraction of second atom, 25 by 100. So you will get 35.5 AMU. So the atomic mass or the average atomic mass of the chlorine, you will take 35 by 5 AMU. Why you are taking the 35 by 5? Why you are not taking 35 or 37? Because chlorine is found in nature in two forms. One form is 1735, another form is 1737.
Yeah.
After that, isobars. So isobars have same mass number, different atomic number. This is very easy again. So take the example. Here is carbon, here is nitrogen.
Yeah.
Carbon, nitrogen. So basically these are the atoms of different element. Isobars are the atoms of not same element. These are the atoms. This is carbon atom. This is nitrogen atom. This is carbon atom. This is nitrogen atom. So basically, for isobars, what you can say? Atoms of different element.
Yeah.
Atoms of different element. Okay. Mass number same, atomic number different. So check the mass number of carbon atom and nitrogen atom. So mass number is 14, mass number is 14, atomic number is 6, atomic number is 7. So mass number is same, atomic number is different. So these are the isobars. Another example, argon and calcium. Mass number same, atomic number different, isobars. After that, isotones. So isotones also the atoms of different element whose nucleus have same number of neutrons, same number of neutrons. And how to calculate number of neutrons? A minus Z. Number of neutrons A minus Z means A minus Z value will be same. Okay, A minus Z value will be same. For example, this is lithium and beryllium. Lithium and beryllium.
Yeah.
Now atomic number different, mass number is also different. Now we will check number of neutrons. How many neutrons will be there? 7 minus 3,
Yeah.
4 neutrons are there. 8 minus 4, 4 neutrons are there. Understanding now?
Yes, sir.
Isotones.
So your voice is lagging.
Isobars. Actually, there is a problem with my internet. Okay, I'm changing my connection. Okay.
Okay.
Hello. Hello.
Yes, sir.
Okay, now it is okay.
Yes, sir.
Little better.
Yes.
Okay. So these are the okay. So isobars having same number of
Neutrons.
same number of neutrons.
Yeah.
Isotones. So after that, from is here, start from here. Isotones is having same number of neutrons.
Yeah.
Isotones having same number of neutrons. Isobars having same number of nucleons. Because mass number is same means you can say same number of nucleons.
Yes, sir.
Please tell me if there is any problem, okay, with my voice, means
Okay.
if it
Okay,
is
sir.
breaking or all that.
All right.
Okay. So isobars, same number of nucleons, and isotopes, atomic number is same, means same number of protons. Okay, same number of protons. And why we are calculating the fractional mass? Because of different isotopes of same element.
Yeah.
And element, always remember, element will be decided by the atomic number. So there is a note point here. Element will be decided by atomic number Z. Okay, first you should take the screenshots, then we will discuss the next topic.
Okay. Done, sir.
Okay.
Done, sir. Done, sir. Done, sir. You're done. Done, sir. Done, sir. Done, sir. You're done. Yeah, done, sir.
Okay. This is the example of isotones.
Done, sir.
Okay. So now we will discuss the nuclear shapes, size, and density. What is the shape of nucleus? Basically, for shape, we can say that for all practical purposes, shape of nucleus is considered as spherical. So basically, shape of the nucleus is considered as spherical.
Yeah.
Okay, but in actual, it is found that there is some deviation. It is approximately less than or equal to 10%. Nucleus is not a perfect sphere. Now, size of the nucleus, experiment shows that volume of the nucleus is directly proportional to number of nucleons in nucleus. Let's do it. V is directly proportional to A. Okay.
Yes.
V is the volume. Okay. A is the mass number. Because number of nucleons means mass number, no? Number of nucleons means mass number. So volume of the nucleus, how we will calculate the volume of the nucleus? This nucleus we are considering sphere for the calculation or for the practical purposes. So nucleus is a sphere and having suppose radius r. So volume of the nucleus will be 4/3 pi r cube. So volume of the nucleus is directly proportional to A. So volume is this directly proportional to A. So from here you can say you can calculate the value of r cube. So r cube is directly proportional to, it will be 3a divided by 4 pi. So this 4 pi is constant. So you can say radius cube is directly proportional to a. From here you can calculate r. R is directly proportional to a to the power 1/3. From this proportionality, when you will remove this proportionality sign, this will be the constant. R is equal to r naught a to the power 1/3. What is r? Radius of the nucleus, and this constant is r naught is a constant for all nucleus, and a is the atomic. A is the mass number. A is the mass number, and the value of the r naught constant is 1.2 into 10 to the power minus 15, and 10 to the power minus 15 is equal to 1 Fermi. Okay.
Okay.
So r naught you can write 1.2 Fermi. Okay. So basically you have new formula, r is equal to r naught a to the power 1/3. So with this formula you can calculate the radius of the nucleus. R is equal to r naught a to the power 1/3. R is equal to r naught a to the power 1/3. R is the radius of the nucleus.
Yeah.
R naught is the constant having the value 1.2 femtometer or Fermi, and A is the mass number of the nucleus or for which you are calculating the radius. Now after that, density of the nucleus or nuclear density. We know that density is the density of anything, any substance is mass divided by volume, mass of the substance divided by the volume of the substance. So basically, for density, you can say mass of the nucleus divided by the volume of the nucleus. Density is equal to mass upon volume. So mass of the nucleus is basically how we calculate the mass of the nucleus. A into 1 AMU, I told you there.
Yeah.
I told you now.
Yeah.
How to calculate the mass, atomic mass or mass of the nucleus. Mass of the nucleus is A into 1 AMU.
Yes.
So A into 1 AMU divided by volume. Volume of the nucleus we know 4/3 pi r cube. Okay. So
Yeah.
now from here, it is A into 1 AMU. It is 4/3 pi. In terms of this R, I can write this value R naught A to the power 1/3.
Yeah.
R naught A to the power 1/3 and cube of this. Okay. So from here, A into 1 AMU, it will be 4/3 pi. This is R naught cube into A. R naught cube into A. So from here, A and A will be cancelled out. So you will have 1 AMU divided by 4/3 pi R naught cube. So R naught value we know 4/3, pi we know. Okay, 1 AMU we know. And 1 AMU I told you 1.67 into 10 to the minus 27 kg. 4/3 pi R naught cube. So put the value of R naught. So approximately the density of the nucleus is very, very large. That is 2 into 10 to the power 17 kg per meter cube. If you will compare this density with density of water, so density of water is 10 to the power 3 and density of nucleus is 10 to the power 70. So very large density the nucleus have.
Yeah.
Large density means in small space, large mass is there.
Yes.
In a small space, in a small space, the large mass is there. Now we will do one question on it. Okay, so I already solved this question. So again, we will solve this question. This is the question from NCERT. Okay, so they are saying that find the nuclear density for iron given mass of the iron nuclei is equal to 55.85 AMU. Mu means AMU. So mass of the nuclei is given. And one more thing is given, mass number. Mass number is given. A is the mass number. So what do we have to find the nuclear density for iron? So for iron, nuclear density is represented by rho. So mass of the iron nucleus, mass of iron nucleus divided by volume of iron nucleus. Now mass of the nucleus is given 55.85 AMU. Volume of the nucleus is spherical. We assume that nucleus, this is suppose iron nucleus, spherical in shape having the radius r. So the volume of this will be 4/3 y into r cube. Now we have one formula for the radius. R is equal to r naught a to the power 1/3. So from here we can calculate r cube. So it will become r naught cube into a.
Yeah.
So now put this r cube in this formula. So density of the nucleus will be 55.85 AMU. This is divided by 4/3 pi r cube can be written as r naught cube into a. R naught cube into a. And we know the value of r naught. We know the value of r naught. What is the value of r naught? R naught value is this 1.2
Yeah.
into 10 to the power minus 15 meter. Okay. So put all the values. Rho is equal to 55.85 and 1 AMU is 1.67 into 10 to the power minus 27 kg divided by 4 upon 3 pi r naught cube means 1.2 into 10 to the power minus 15 cube of it. What is the mass number of iron given? 56.
Yeah.
Is 56. So when you will calculate, approximately you will get the answer 2.2 into 10 to the power 17 kg per meter cube. This is the answer we will get. So now please take the screenshot. Then we will discuss the mass energy equivalence. So I'm zooming out.
Okay.
Okay, just a minute. Now take it.
Done. So
Okay, please take the screenshot.
can you scroll down? Sir?
Yeah.
No, sir. Can you scroll so that I can see? Yeah, this. Yeah. Done.
Okay.
Done. Done.
Okay. Now we will discuss the mass energy equivalence. So mass energy equivalence. In 1905, Einstein, in his special theory of relativity, suggested that mass is a form of energy, and he predicted that mass and energy are equivalent. So what is the meaning of mass and energy are equivalent? Okay. With this example, you will understand. If the energy of the body is increased by amount E, then its mass is increased by M, and that M is equal to E divided by C square. For example, this is a mass M here. This is a mass M. So I am giving it energy. Suppose I am giving it the energy of 10 to the power 5 joule.
Yeah.
So according to this, or according to Einstein's special theory of relativity, if I am giving energy to this mass, if I am giving energy to this mass, so due to this energy, the mass will increase. The mass will increase, and that increase in mass, that increase in mass is equal to energy given E divided by C square. Energy given is 10 to the power 5 and C is the speed of light in vacuum. So this much amount of mass will increase. So m, what is m? M is the increase in mass. And E is the energy given. Energy increased. E is equal to mc square. No? You know.
Yeah.
You know E is equal to mc. This
Yeah.
is
Yes.
that.
Oh.
Basically, Einstein given this equation in this form. But
Okay.
this equation becomes famous in this form. E is equal to mc square.
MC square.
Later, I will tell you what is the meaning of this also.
Okay.
First, you should understand the meaning of this. M is equal to E by C square, where M is the increase in mass, E is the energy given, and C square is the trade-off. Okay. One question is there. So this is the question. Find the increase in mass of 1 kg of water when it absorbs this much of energy. 1 kg of water is there.
Yeah.
This is a glass, suppose. In this glass, this is a container, you can say. And in this container, the 1 kg of water is there. And this is absorbing the energy of 4.2 into 10 to the power 3 joule. They are asking what is the increase in mass of the water. So increase in mass of the water is equal to energy given divided by C square.
Yeah.
This M is not the usual mass of the water. M is increase in mass.
Okay.
This is increase in mass. What is this? Energy given or energy absorbed?
Yeah.
And C value is 3 into 10 to the power 8 meter per second. Now increase in mass of the water, you will get now. What is the energy given? Tell me first. What is the energy? What is the value of energy given to the water?
4.
This energy, na?
Yeah.
4.2 into 10 to the power
3 joules.
4.2 into 10 to the power 3 joules. Okay.
Yeah.
And this is divided by C square, means 3 into 10 to the power 8 square. Approximately, this answer will come out to be 4.7 into 10 to the power minus 14 kg. This is almost zero. This mass is almost zero, no? 4.7, it will be 0.000300.
Yes.
47. So it is almost zero. But this value is very, very, very less. But this is the value, na? So we can say that this mass M, this M or increase in mass is very small. But not zero. That is why in general or practical life, in our daily life, we are giving the energy, but we are not seeing that the mass is increasing. Suppose you are there in front of me. Suppose I have given you the energy of 10 to the power 5 joule. So will your mass will increase? Will you? According to the Einstein, it will increase, but that increase in mass will be negligible. So that will not be observed or that will not be felt by you or me. Okay. But there will be increase in mass. This is little bit strange thing. If you are giving energy, means the object mass will increase. Now what is the significance of E is equal to mc square? E is equal to mc square means if m mass disappears, E energy will release. If m mass disappear, E energy will release.
Yes.
Somehow, if there is a mass disappears,
Yeah.
so the amount of energy release will be given by E is equal to mc square. Okay, now we will discuss the mass defect and the binding energy. Mass defect and the binding energy. Now, what is the mass defect? First, we will discuss the mass defect. It is observed that suppose these are the nucleons, neutron, proton, neutron, proton, neutron, proton. These are the nucleons, and after combining these nucleons, there will be the formation of nucleus. So nucleus is formed from or by nucleons.
Yeah.
Inside the nucleus, neutrons and protons are there.
Yes.
Okay. So we are talking about the formation of the nucleus. So initially there will be nucleons and they will combine somehow and nucleus will form. And it is found that mass of nucleons is greater than the mass of the nucleus. So this is the nucleus formation. These are the nucleons.
Yeah.
And this is the nucleus.
Yes.
So mass of, it is found that mass of the nucleons is greater than the mass of the nucleus. So here some mass is disappearing.
Yes.
Some mass is disappearing. And if some mass is disappearing means if mass disappears, what happens? According to E is equal to mc square, energy will release.
Yeah.
Okay. So some mass disappear during the formation of nucleus. The mass that disappears is known as the mass defect. Now we will discuss the expression for the mass defect. Suppose this is the element X, atomic number Z, mass number A. So in this element, number of proton will be Z. Number of neutrons will be A minus Z, and number of nucleons, that will be number of protons plus number of neutrons. So mass defect is mass of nucleons minus mass of nucleus.
Yeah.
That will be the mass that disappeared.
Yeah.
Okay. So mass of nucleons minus mass of nucleus. And what is the mass of nucleons? Mass of nucleon means mass of proton plus mass of neutrons. Inside the nucleons are protons and neutrons now.
Yes.
Okay. So mass of nucleons is equal to mass of protons plus mass of neutrons minus mass of nucleus. Okay. So mass of proton is given by atomic number multiplied by mass of one proton. MP here, azan time, so I will wait for 1 minute.
Okay.
So this m suffix p will be the mass of single proton. Mass of single proton. So total mass of the protons inside the nucleus will be the number of protons multiplied by the mass of proton. Means mass of proton will be given by Z into mp. Similarly, mass of nucleons will be given by number of nucleons multiplied by mass of a single nucleon. So A minus Z are the number of nucleons multiplied by mass of single nucleon minus mass of the nucleus X. Nucleus of this element X. So mass of m suffix n is equal to mass of single nucleus. Mass of single nucleus. So basically this formula we will get for to calculate the mass defect. Now after that, binding energy. What is the binding energy? Delta E is the symbol for the binding energy. So during the formation of the nucleus, formation of nucleus, I told you there will be the mass defect. Some mass will disappear. And I told you according to this equation, if some mass will disappear, then energy will release corresponding to that mass. So delta M mass is the mass defect here in the formation of nucleus. So basically this delta E is the binding energy, and that is given by delta M into C square. So that is the binding energy. So binding energy, to calculate the binding energy is very easy. Delta M into C square. Put the value of delta M. We have this delta M into C square. This is the formula to calculate the binding energy. Now, suppose see this equation in this way, in this direction. So this delta E is basically, we can say, is the energy given to the nucleus. Energy given to the nucleus to break this nucleus, okay, so that we will get again nucleons. Okay, so basically it is the amount of energy released. It is the amount of energy released is the amount of energy released to separate all nucleons from the nucleus. Basically it is the amount of energy given. Amount of energy given to separate all nucleons from the nucleus. Basically this is the nucleus, and inside the nucleus the nucleons are bounded. We want if we want these nucleon to be free, we have to give some energy, and that energy basically the binding energy. Okay, it is the amount of energy given to separate all nucleons from the nucleus. Okay, and the binding energy bounds the nucleus, bounds the nucleons in the nucleus. So these nucleons are bounded in the nucleus due to the binding energy. So one question we will solve on binding energy. This is the question. Find the binding energy associated with mass defect of 1 AMU. Mass defect of 1 AMU. So mass defect is given, and corresponding to that mass, we have to find the energy. Energy associated with mass defect. And what is that energy? Binding energy. So the formula to calculate the binding energy is delta E is equal to delta M into C square. What is the mass defect given? 1 AMU. 1 AMU. So we can convert 1 AMU into kg. 1 AMU is 1.6 into 10 to the power minus 27 kg. So delta M will be 1.67 into 10 to the power minus 27 kg. And C square means 3 into 10 to the power 8 and square of it. Square of it. Now, if you want to convert this value into electron volt, so you will multiply this term. Basically, this value is in joule. Now, if you want to convert this value into electron volt, so what you have to do, you will multiply this with 1.6 into 10 to the power 19. This will be in the electron volt. This will be in the electron volt. If you will multiply this value, because in 1 electron volt, there is 1.6 into 10 to the power minus 19 joule. So when you will calculate 1 joule from here, it will be 1.6, I think. It will be just a minute, minus 19. So it will be 1 divided by 1.6. Okay, just a minute. This value is in joule, okay?
Okay.
This value is in joule. Now we know that in 1 electron volt, there is 1.6 into 10 to the power minus 19. 1.6 into 10 to the power minus 19 joule. So if you will find how much, if you want to convert joule into electron volt, so what you have to do, 1 joule will be 1 upon 1.6 into 10 to the power 19 electron volt. So this value you have to multiply 1 upon 1.6 into 10 to the power 19. So this value will be in electron volt. And if you want to convert this value into mega electron volt, so you have to multiply this value with 10 to the power minus 6. So it will be in mega electron volt. Mega electron volt. So on calculating, this value is found to be 931.5 mega electron volt. Now you have to remember this. When there is a mass defect of 1 AMU, this much of energy will release. Okay. So note, if mass defect of 1 AMU, then 931.5 mega electron volt energy released. Okay, so basically, if mass defect will be of 1 AMU, then how much energy will release? 931.5. If 2 AMU will be there, 2 AMU mass defect will be there, so it will be 2 into 931.5 mega electron volt. If mass defect will be 5 AMU, then energy release will be 5 into 931.5 mega electron volt. So this formula we can make delta E means the energy release is equal to delta M, and delta M value you will put in AMU and multiply by 931.5 and you will get the value in mega electron volt. For example, if mass defect is delta M, you want to find the energy release. So what you will do? You will apply this formula, delta M into 931.5. So delta M into 931.5 mega electron volt. What is the value of delta M? 0.002 into this, and this will be your answer in mega electron volt. This will be your answer in mega electron volt.
Okay.
Okay, take the screenshot.
Done.
Okay.
Done. So can you just show me the answers? The full, yeah. That's done. Yeah, done. Done.
Okay.
Done. Done. Yeah, done. Oh, yeah.
Done?
Yes.
Okay. Okay, so this is the question, so you can see. So after that, the next topic is nuclear stability and binding energy per nucleon. So nuclear stability means how stable the nucleus is.
Okay.
So this is the experimental data. This is the experimental data. So the binding energy of heavy hydrogen means 1s2.
Okay.
1 is the atomic number,
Yeah.
mass number is 2. Heavy hydrogen. So in this heavy hydrogen, how many protons are there? 1 proton and 1 neutron. Okay. So the binding energy of heavy hydrogen is 1.1 mega electron volt. Okay.
Okay.
It is found that binding energy of heavy hydrogen is found to be 1.1 mega electron volt, and the binding energy of uranium 238 is
Yes.
found to be 1800 okay, 1800 mega electron volt. So the binding energy of uranium 238 is greater than the binding energy of hydrogen. So see the next line. Binding energy increases with increase in mass number. If you will increase the mass number,
Yeah.
then the binding energy will increase. It means, this means, okay, after that, if you will find the binding energy of iron 56,
Yeah.
so it is 492 mega electron volt. Okay. Basically, we should remove all these things. Mass number, now it's fine. After that, binding energy of iron is this 492 mega electron volt. 492 mega electron volt. So this is the iron and this is uranium 238. So binding energy of, if I will compare the stability
Yeah.
of uranium nucleus and iron nucleus, so which one will be more stable? Binding energy of uranium 238 is this,
Yeah.
and binding energy of iron 56 is this.
Hmm.
So which have the more binding energy?
Uranium, right?
Uranium. So which will be more stable?
This one, iron.
Yeah, iron. The reason, but binding energy of uranium 238 is more.
Yeah.
But then also the iron 56 is stable than uranium. We will see that. The reason is that the binding energy per nucleon of iron is greater than binding energy per nucleon of uranium 238. Basically, binding energy is not the criteria.
Yeah.
Binding energy is not the criteria for the stability of the nucleus. It is the binding energy per nucleon that will decide which nucleus will be more stable.
Hmm.
Is more stable than uranium 238 because for iron 56 binding energy per nucleon is greater than uranium 238. So there is a binding energy curve. So basically, now we can say that stability of nucleus is depending upon binding energy per nucleon. Binding energy per nucleon. Okay, binding energy per nucleon. So stability will not depend upon the binding energy. It will depend upon binding energy per nucleon.
Yeah.
How much is the binding energy divided by how many nucleons are there in a particular nucleus.
Yeah.
So, okay. After this is the curve. This is the curve between the binding energy per nucleon versus the mass number. So you can see here iron is having the maximum binding energy per nucleon.
Yes. Yeah.
And least is for hydrogen 1, 2. Okay.
Yeah.
So this curve is like this.
Yeah.
From, you can say, generally you can say from atomic mass, from mass number 0 to 50, approximately from atomic number 0 to 56, you can say the binding energy first increasing.
Yes.
And after that it is decreasing.
Yes.
So the whole observation of this graph I have written. What will be the observation of this? So from A50 to A80, from here to here.
Yeah.
From here to here, see the curve. This is the curve. So binding energy per nucleon is approximately equal to 8.5 mega electron volt. So from here to here, approximately the binding energy per nucleon is 8.5 mega electron volt. These nucleus are less stable nucleus. So from 50 to 80, the nucleus are less stable nucleus.
Yeah.
Except iron. Second. Oh, sorry. These nucleus are stable nucleus because binding energy per nucleon is greater, 8.5.
Yeah.
After that, iron. Having the mass number 56, binding energy per nucleon is 8.8 mega electron volt. Has the highest binding energy per nucleon and hence it is most stable. For A greater than 80, binding energy per nucleon decreases slowly, and for A is equal to 238, it reaches to 7.6 mega electron volt. These heavy nuclei are unstable. They try to gain stability through nuclear fusion. Basically, from A greater than 80, 80 will be somewhere here. So from here to here, you can see the binding energy per nucleon is decreasing, and it is
Yes.
minimum at uranium 238. So
Yeah.
these heavier nucleus are less stable. For gaining stability, they will try to achieve the nuclear fission. We will discuss what is nuclear fusion, what is nuclear fission.
Yeah.
Okay. For A less than 50, binding energy per nucleon decreases sharply and reaches to 1.1 mega electron volt for hydrogen 2. So from less than 50, from here to here, there you can see binding energy per nucleon is decreasing sharply, and this is
Yes.
less for this.
Yeah.
So A less than 50, binding energy per nucleon decreases sharply and reaches to 1.1 mega electron volt for hydrogen 2. These nuclei are light and unstable. They try to gain stability through nuclear fusion. Basically, the heavier nuclei will try to achieve the nuclear fission because they are less stable, and
Yeah.
those nuclei which are less stable and they are the smaller nuclei, or you can say light nuclei. So they will try to achieve the nuclear fission to get the stability. Okay. Okay, so take the screenshot.
Okay. Done.
Okay.
Done.
Okay.
Done.
Okay.
Done. Yeah, done.
Okay. So nuclear fission is the next topic.
Yeah.
So basically nuclear fission, this is the bigger nucleus, and
Yeah.
this will splitting into smaller nuclei. This is basically the nuclear fission. So nuclear fission is a nuclear reaction in which a heavy nucleus splits into two or more smaller lighter nuclei. So this is a heavier nucleus, and this will split into two smaller nuclei. These smaller nuclei are known as the daughter nuclei. Most of the fissions are binary. Binary means after splitting, we will get two nuclei.
Yeah.
4 out of 1,000 are ternary. Ternary means after splitting, we will get 3 nuclei. So 4 out of 1,000 are ternary, but
Yeah.
most of the fissions are binary.
Okay.
The daughter nuclei are of comparable size. If you will compare the size of this and this, these nuclei will be of comparable size. Okay.
Okay.
Two types of fission we will see. Spontaneous fission is the radioactivity, and this is rated from your syllabus. So we will discuss the induced fission. Okay, induced fission is induced by either proton, or it is induced by alpha particle, or either it is induced by the neutron. Induced means some starting force will be required, and after that it will be self-propagated. After that it will be self-propagated. For example, this is the uranium 235,
So
and
your
this is the
voice is
thermal
lagging.
neutron. My voice is lagging.
Yes.
Okay. Okay. Now it's fine.
Yes.
So this is a uranium 235. So we are discussing basically the induced fission. We are discussing the induced fission. Okay, so I will discuss this tomorrow because I am having next class in 5 minutes. Okay.
Okay, sir.
So you should take. Have you taken the screenshot? Oh, please take
No,
this.
no,
Screenshot.
sir.
Please take this screenshot. I will start tomorrow from here.
Okay.
Induced fission. So tomorrow this chapter